Hello, and welcome to our talk on Rollercoaster. My name is Daniel, and I'm a PhD student at the University of Cambridge. This is a collaborative work that I've done together with Martin Kleppmann and my supervisor Alastair Beresford. I really enjoyed working on this project, and I hope this talk gets you excited as well. I would start with a short introduction into the problem domain. Afterwards, I will present our basic idea and some selected extensions. Our work is in the field of mixed networks. For those unfamiliar, mixed networks are a basic class of anonymity networks. They allow to hide the relationship between the sender and the recipient of messages. A mixed network does so by encrypting the messages in multiple layers and sending them over multiple hops. Every hop is able to remove only the outermost layer and reach the address of the next hop from the included message header. So every hop only knows its direct predecessor and successor. In addition, messages are mixed with other messages at those hops. That makes it hard for an adversary to correlate incoming and outgoing messages. We generally assume a global adversary that can observe all traffic and can compromise a subset of mixed nodes. In our paper, we are building upon Loopix, which we consider a very modern and practical design. This is the infrastructure that we will be working with. The application area is Group-Multicast. We assume that there is an established group of people, and any member in that group might want to send a message to all other members in that group. A potential application for Group-Multicast are decentralized collaborative applications, such as text editing. Since edits can depend on previous changes, we want the latency to be low, ideally not much larger than 10 seconds. Imagine, for instance, that you're adding some words to a paragraph and another person is reordering all paragraphs in a chapter. We still want to achieve the same security guarantees that mixed networks provide. And in addition to that, we are concerned about the privacy of groups. An adversary, for instance, must not be able to tell anything about group membership, including group sizes. The mixed networks that we work with try to prevent an adversary from learning whether there's any communication happening at all at any given time. This property is often called unobservable communication. It is achieved through cover traffic. The idea is that the pattern and the appearance of the outgoing messages must not leak any information. We hide the appearance by making sure that all outgoing packets are always padded to the same size. We hide the patterns by sending the packets either at fixed intervals or with random delays. In both cases, this happens independent of whether there's meaningful payloads to be sent at any given time or not. When there's no payload message at such a send event, an empty cover message is sent instead. And when there's too many payload messages, they are queued and sent one after the other. Let's now consider two naive solutions for Group-Multicast before we talk about Rollercoaster. The first one would be to send each message individually to each group member. However, this can very quickly overwhelm the payload queue. For instance, let's consider a group with 100 members, and that all send events are on average 5 seconds apart. The message for the final recipient would only be sent after 8 minutes. What's more, if the application generates more than one payload every 8 minutes, then this would mean that the payload will struggle to fully recover. The other simple idea would be to have the messages multiplied at one of the mixed nodes. However, this comes with two problems. First, the mixed node that does the multiplication would learn about the group size. This is in contradiction to our security goals. The second one is a practical one. We would need to increase the size of all messages to be able to fit the included messages in there. And since each of the included n messages would need to be routed independently after the multiplication step, we would need to add n headers and n differently encrypted payloads. And note that this depends on the maximum group size that we want to support in that network. Most people will not be part of such large groups and therefore pay an unfair overhead for participation. I will now explain the basic idea behind Rollercoaster. Due to the scope of this talk, it's simplified and we provide much more details in our paper. The idea is that after the original sender, which we often call the source, sends the first message, the first recipient can actually help sharing it. And if all members carefully follow the plan, the group of people who already received the message doubles with every round. As a result, the total time to distribute the message is logarithmic in the total group size, without doing any changes to the underlying network. In our paper, we look in more detail at how this interacts with the constraint sets by mixed networks. And I now present two extensions that make our basic idea more robust and more efficient. The first extension deals with fault tolerance, in particular when clients are offline. Clients might be offline just temporarily, for instance when they have no signal coverage, or indefinitely when a device breaks or gets lost. If that happens, that client cannot participate in distributing the message anymore. In this example, the faulty recipient breaks the forwarding tree for 3 other members in that group. We fix this by requiring every node to send an acknowledgement message to the source node. We chose the source node for overlooking this process as it has the highest incentive to see through the eventual delivery of its own messages. So the source node will have timeouts for all the nodes in the forwarding tree. And when it notices that it misses an acknowledgement message, it sends the same message that failed to another node. Through a special role field in the header, the new node is instructed to carry out the job that the faulty node was supposed to do. And of course, the source node will reset all dependent timeouts accordingly. We can also have timeouts for indirect recipients, and that way the source can detect also when the forwarding node is acting in a Byzantine faulty manner. As an optimization, the source node remembers which node it has seen most recently and can prioritize those for the more important forwarding roles. Everything we talked about so far can be deployed without changes to the underlying network infrastructure. This is great because we can benefit from an already existing anonymity set and user base. However, we can squeeze out a bit more efficiency when considering some minor changes. This extension picks up the mixed node multicast idea that we've seen in the orange slides. However, instead of grouping the messages for all group members together, we simply group the P most recent sent events at each client. For now, let's assume P equals 2. As a result, every outgoing message is now twice the usual size. And differently to the naive approach, the multiplying nodes won't learn the group size. When the messages are multiplied, the included messages are delayed and mixed independently based on their respective headers. This extension is particularly helpful in dealing with bursts of payload messages. We found that this construction was surprisingly intricate. This is because the multiplying node needs to add padding to the outgoing messages, and the header of the included messages still need to successfully check the integrity of the entire message, even when it is decrypted by the subsequent hops. Let's now have a look at how Rollercoaster performs. For our evaluation, we have implemented a deterministic simulator. This seemed to us to be a sensible choice, as the underlying network was already practically evaluated in the Loopix paper. Compared to a real-world prototype, it makes our results fully reproducible, and it allowed us to execute them 500 times faster than if we would have done in real time. This enabled us to include much more and much larger scenarios in our paper. This graph shows how the performance of different algorithms for scenarios behaved where all clients were online throughout. The message latency is measured on the application layer, from when the message enters the payload queue at the source to when it is delivered to the recipients. The blue boxes are for the sequential unicast technique that we have seen at the very beginning in the orange slides. The green boxes show the results for Rollercoaster. The light ones without the p-restricted multicast extensions, and the darker ones have p equal 2. The x-axis shows different group sizes from 32 to 256, and the y-axis shows the observed latency up to 110 seconds. what we see is that as the unicast approach grows linearly, it quickly results in latencies that are too large for interactive applications. Meanwhile, the rollercoaster latency are mostly around 10 seconds, good enough for interactive text editing. However, once some of the nodes can be offline, the very basic rollercoaster idea does not perform that well anymore. Here we see 2 box plots for different group sizes. Each shows 3 groups for scenarios with different ratios between online and offline time for the clients. The y-axis is now log scale and ranges up to thousands of seconds. Again, we have blue for unicast and green for the basic rollercoaster algorithm. And what we see is the basic rollercoaster one is struggling, and we see very dramatic latencies. This is, for instance, because when a forwarding node is offline for 2 hours, all its children will also only receive the message 2 hours late. The orange bars show the results for when we add fault tolerance. And what we see is that adding timeouts and the role reassignment does actually very well prevent this degradation. And with this extension, Rollercoaster still outperforms unicast consistently. There are plenty more scenarios in the paper, for instance for payload bursts and membership in multiple groups. This has been a short talk about our work. If this was interesting to you, we have plenty more details in our paper, and we would be particularly happy if our technical artifacts enable more research and experiments in this area. Thank you very much for watching, and please do not hesitate to reach out to us with any feedback or questions.